All right, so heat calculations. We've talked about two different types of line segments on this curve, right? So we have to consider two different energy calculations on a heating or a cooling curve. The first one we've already talked about. So during a phase change, the energy is going towards breaking intermolecular forces. So that's using, what is this delta H? What do we call that delta H? Does anyone remember? It's what heat? Heat.
Increase, right?
It's molar heat. Remember, molar heat of fusion, molar heat of vaporization. Right, these are terms we have heard before. Okay, so it's going to be the molar heat times either the number of moles or the number of grams. How do I know if I'm using moles or grams?
Well, you see. If there's a gram,
It will tell you.
It won't tell you. You have to look at the units of your molar heat. If you're in units of kilojoules per mole, you're multiplying by moles. If you're in kilojoules per gram, you're multiplying by grams. Okay. Now the other type of Q just stands for heat or energy. So as temperature increases, right, energy is going into raising the kinetic energy of the molecules. Right, that is a change in temperature, so we have to use a different formula. So temperature is the measure of kinetic energy of a substance. So the higher the temperature, what can you say about the kinetic energy?
higher.
Higher. Is that actually on there? I don't think it is. No, that's fine. Whatever. Review. So, specific heat uses a different formula. And I'm going to explain this in a second, but first, specific heat. Right? It is the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius.
Specific.
Now, I also say that it's 1 degree Kelvin, and the reason why is because this is a difference in temperature. The difference between 1 degree Celsius and 1 degree Kelvin is the same. So let's take 25 degrees Celsius, and it's going to heat to
25.
I don't know, 56. 56 degrees Celsius. Okay. What is 56 minus 25? 31 degrees Celsius. Right, that's the change. Okay. Now, if I convert this to Kelvin, how do I take Celsius and convert it to Kelvin? I have to add a number.
273.
273. So 25 plus 273 is 298 Kelvin. And then 56 plus 273 is going to be 330.
4. No.
No, hold on. 329. Yes. All right, Kelvin. What's 329 minus 298?
31.
31 Kelvin. So the change is the same, even though the actual values
Is that
are
an E or
different.
D?
What? That's a delta.
Delta, okay. Well, I guess that
It's a bad delta, but it's a delta.
Yeah. Sorry.
Yes. Yeah. What's wrong with you?
I drank the whole thing.
I'm not too sure why you go.
Okay. Ooh, let me pull this back up.
Writing my name on it.
You fill up your water bottle.
Okay, so
Should I,
typically the units for specific heat, right, which is abbreviated CP, right, the P just stands for at constant pressure, which we normally are. We don't exist in a vacuum, so. Anyway, so it's in units of joules per gram degree Celsius, right? That is joules all over the gram degree Celsius, okay? Both of these are in the denominator. Joules is the SI unit for what? Energy. There's also another unit of energy that you guys are actually way more familiar with. The calorie.
What are you trying to say?
That the U.S. doesn't use the metric system is what I'm trying to tell you.
Why?
I asked myself that. To make my life harder.
Literally just gonna snatch it all away.
But actually.
Yes.
Alright, please write this in the margin somewhere. Alright, please write this in the margin. 1 calorie, and that's calorie with a lowercase c, but 1 calorie is equal to 4.18 joules.
Someone turn their phone off. It's Ethan.
Ethan.
So 1 calorie is equal to 4.18 joules.
Wow. Wait, which kind of calorie were you talking
What kind of jewel we talking
Lowercase c. Okay. Before we move on, I just want to give you guys a little background on the whole lowercase versus uppercase calorie. So, does anyone have any type of like protein bar or anything with a nutritional value on it?
How about
Can you pull it out?
I have Doritos.
I don't want to know the calorie count.
Yeah, if you,
All right, can you look on the back and where it says how many calories it is? How many calories, first of all?
170.
170 calories, and is that calories with a lowercase or an uppercase c?
Jane Steak commenting.
Uppercase.
What the props
Okay.
for chem class?
Okay, so on your little nutritional facts, all right, this is trying to make you feel good about yourself kind of thing. The calories that we talk about in the U.S. are uppercase calories. That is actually 1 kilocalorie. Okay, so instead of being 170 calories, it's actually 170,000 calories.
Wow.
That being said, your
That's
daily
all right.
intake is supposed to be 2,000 calories, right, for a normal, non-athletic human being.
2,000.
That's actually 2 million calories, right, for the actual unit of calories.
Wait, so it takes 4.18 joules. So we can
Nothing
measure-
really. It's just that the U.S. tries to make you feel better about your calorie intake by dividing it all by 1,000.
Oh, even though
This is just 170 calories. Well, no. It's 170,000 calories out of the 2 million you need each day. But instead, you're saying, oh, it's 170 out of just 2,000.
it's the same ratio.
Oh, yeah, it is. But it's all just mind games.
I know it's like-
What kind of other mind games?
I was pretty sure it did.
Oh, my Coke. Hold on, let's look at my Coke.
You have Coke?
Coca-Cola. No, it's uppercase calories.
It is?
Yeah.
Aren't they always uppercase? Like, what
Yeah,
is
it should be.
So we can measure our food in joules.
In fact, if we had more time in the year, we would set stuff on fire and figure out how much energy was actually in them. Let's do that after the SOL.
Wait, what do you mean? We can.
You burn it and you see how much energy was released.
Well, wait, what do you mean they don't have enough time? After us.
Because I have to. I'm already taking a week out of Tiger 3.
Oh, I thought you were talking about like actual scientists.
Oh no, I meant us.
I was like, we don't have enough time in the year.
No, we do. All right. So a specific heat that you have to know, all right, is the specific heat of water. Right, that is 4.18 joules per gram degree Celsius, or just 1 calorie. That's actually where we get the unit for calories. It's big. How many calories?
I don't know. It doesn't say.
Yes, it
Probably
does.
150.
Low Gotti.
That's 150,000 calories. How does that make you feel?
This is chem class,
Special.
not math class.
I want to go to
Ethan, you okay back there?
That's what I was about to
That's a
say.
lot of calories.
Okay. Anyway, so we actually looked at, the standard unit for water, and we actually just made it calories, because why not?
It's simple.
Right?
Really.
Right. So the equation you are going to use, right? The Q is just the heat energy, right? So it's in units of joules or calories. Okay. Times your mass, not moles, but mass, times the specific heat, times the change in temperature. Remember, delta means change. All right. So here's a good way to remember this one. This formula isn't given to you. Okay. But
Oh.
okay. So when you guys go into college, right, the test that you have to take, right, to go to college is you have to take a test. The SAT. That stands for Scholastic Aptitude Test, for those of you guys who didn't know that. Right?
I knew
Now, who's seen Legally Blonde? Yeah. Does anyone remember the test that she's studying for?
No.
It's the LSAT, right? That stands for Law School Aptitude Test. Does anyone know the test you have to take to get into medical school?
MCAT.
It's the MCAT for Medical College Aptitude Test. Okay, they actually make sense when you think about it. Anyway, I call this equation, and actually you'll hear this quite often. This is the MCAT equation. Right? Take out the P because it's not necessary. So it's MC. The delta looks like an A. T. MCAT. Mass times specific heat times the change in temperature.
Why is it called medical college and not medical school?
College versus university has to do with size and graduate programs and things like that.
Mm-hmm.
So within a university, you have different colleges.
What?
What?
So, for example, I went to the University of Virginia,
University.
but I was in, the College of Arts and Sciences.
What?
Yeah.
You know, I got a UVA physio I found.
What? So that means
Sorry,
there's
okay.
multiple colleges
Cool story.
on the
Dylan?
Just
Yeah, the
saying.
university has multiple other places.
Yeah.
Like,
So then, if you just go to a normal college, it'll be like.
So, for example, there's the College of William and Mary. It's called a college because it's not big enough to be a university.
Oh, it's not William and Mary.
William and Mary is not a university, it's a college.
I think all those programs that I was showing at University of Virginia, I think it's like the college
Yes.
of the arts and humanities.
Well, no, a College of Arts and Sciences, and within the college, you have departments.
Yeah.
But I thought it was like William and Mary was like so prestigious, but it doesn't even
It
have
is.
the university name.
Well, university has nothing to do with prestige, it has to do with the size.
Ah.
Like how many?
So it could be really big but trash.
Yeah. The Polytechnic Institute and University of whatever tech is called. What is tech called?
Virginia Polytechnic
Institute of Technology.
Oh, it's not even a college. Really? There's no university in there?
I don't know.
I have no idea.
There's no Polytechnic.
But we're totally off topic. Let's get back on topic. Okay. So let's do some examples here.
okay.
So the specific heat capacity of water is 4.186. I just happen to give this to you. In any problem, you just have to know 4.18. How much energy is required to raise the temperature of 250 grams of water from 18 degrees Celsius to 78.5 degrees Celsius?
I don't know.
Wait.
What is all the individual numbers?
We just went over.
So
I just
the
want to-
energy is equal to the mass times the specific heat times the change in temperature.
It's multi.
So I'm looking for the energy Q. Okay. So when I do this, and I really don't know why I switched these two, but it's the mass, so the 250 grams, times the specific heat, the 4.186, and then the change in temperature. Change is defined as what minus what? Just in general, change is final minus initial.
Change is bad. To me, the change is bad.
Right, it's final minus initial. So I started from 18 and I went to the 78.5. So what is my final? The 78.5. That's why it's 78.5 minus 18. Final minus initial.
Wait, so mass is the calorie?
No, mass is the 250 grams.
Wait, that's not the M.
That's mass.
But then what's the 4.1?
That's specific heat.
Oh, you just moved
Yeah,
it.
it switched.
So are we gonna use 4.18 or 8?
In this particular problem, I gave you the 6, so use the 6, but normally just use 4.18.
What is 110? On the periodic table.
I'm reading upside down, so this is hard.
Oh,
I
we're
don't
on.
know that one.
Oh.
And I'm gonna love
Why does it
name
name now,
right?
Why do we only have up until 110? I mean,
Oh yeah, that has a name now. I forget what it
this
is.
old.
Yeah, this is really old.
hey, let me check.
We have the entire 8. Is that 8 or is that
We
7?
have revised
7.
2011. That's not that old.
In chemistry, that's pretty old.
Yeah, pretty old.
Yeah, like
6
7
years.
years.
6
In biology, 2015 is old. In chemistry, 2010 is old. In physics, like the 90s is old.
Okay.
Or
nothing
later.
really changes
Physics
in
doesn't
physics.
change very often. Anyway.
Can we make new laws of physics if we find different planets
do.
that
I gotta make new laws
potentially
of
have?
physics.
Not even different planets. The laws we have now could be wrong. We just haven't found anything to disprove them yet. Law versus a theory. Both of them can be changed. Nothing is absolute. That's part of the nature of science, right? The more information we get, the more we change and, mold our explanations to fit that data. Anyway, okay, so when I do this, I'm going to start by taking the change in temperature. Okay, So when I do this, I get 60.5. Now, when doing addition or subtraction, what is the rule for your sig figs? You go by the least number of sig figs or the least number of decimal places?
Decimal places.
It's decimal places for addition and subtraction. So this has 1 decimal place, this has 1 decimal place, so my answer here has 1 decimal place. Now I'm doing multiplication, right? So when I just multiply it through, it's 63,313.3 joules, okay? But when I'm multiplying, I go by the least number of sig figs. So what does 4.186? How many sig figs? 4. 250.0? 4. 60.5? 3. So I have to put this into 3 sig figs. So that would be 63,300. Just for convenience, I'm actually going to put it into kilojoules. So I'm just going to divide it by 1,000, and that gives me 63.3 kilojoules.
Whoa.
Either way works.
How many calories is that?
Divided by 4.18.
What?
Let me see.
Wait, I thought it was divide. Oh.
Divide this by 4.18.
They eat for.
I don't know, 1,000.
It is, no, it's 15.4.
Like, get an idea.
15.14.
63,313.
Oh, you want me to do it by that number?
Yes.
Too tired
Like,
of
how much
it.
energy,
on
like,
film.
Divided by
Like,
what
an
is it
idea,
again?
like,
4.1.
4.1 calories.
Well, I mean, to give you an idea, to heat up water, just room temperature water to boiling, that's 75 times 4.18.
15,146.72,000.
Joules is small.
Big number.
Relatively.
You don't.
Alright. Alright, guys. Let's go ahead and do another example. So here we have 50 kilojoules of energy being used to heat 250 grams of water to a final temperature of 95 degrees. So what was the initial temperature? Okay. So here I know my Q, I know my mass, okay? I know my specific heat of water is the 4.186. And as far as the change in temperature goes, I know the final, I don't know the initial. Right. Now, here's a question. What are the units of specific heat? For water, it's 4.18 joules per gram degree Celsius. Right? Which means, right, if this is in kilojoules, can I leave it in kilojoules? No, they need to be in the same unit. So down here I actually converted it by just multiplying by 1,000. So it's 50,000 joules. The mass is 250 grams. Specific heat is 4.186. Right? And then the change in temperature is the final 95 minus X, the initial temperature.
Hey, why do we?
Roland just, no, that's not mine. Asking for
Why do we subtract?
Because final minus initial. I know my final. I'm looking for initial.
Is our quiz next class on everything we've learned?
Yep.
everything we learned, like.
So in this unit so far.
Oh, okay.
Including
Even
this. Including this.
Ah,
Oh, good. Misty, you're setting me up to fail.
You're saving
to
yourself.
fail.
You know, there's something called studying, I think.
Yeah, still wouldn't get it.
Alright, let me get through this, guys. Alright,
You're gonna die.
so when I do this, okay, just to lay out the algebra for you guys, you multiply these together. Alright, that gives you 1,046.5. Divide both sides by that 1,046.5. You get 47.8 equals the 95 minus x. How do I solve this here?
Carefully. You subtract 95
And then,
and then make the next positive.
right, so that's one way to do it. The other way I'd say is think about it this way. Alright, add x to both sides, so you move x over here, then subtract 47.8 from the 95. Or subtract the 95 from the 47.8 and multiply by -1. You get the same answer either way. It's 47.2
47.
degrees Celsius.
Cool. That was simple.
You.
Yeah, very.
Alright.
Definitely not gonna mess
I
up.
mean, like, that's a bunch of numbers. It's simple math once you set it up.
It's simple math. The hard part about this is knowing what formula to
Yeah.
use.
But it's the same formula.
Not always. Because, alright, you have to know whether you're using specific heat or molar heat. Okay, so the molar heat of fusion or vaporization is the energy needed to do what?
To heat up.
To evaporate.
Boil.
To change state. Right? To evaporate, to boil, to melt, to freeze. So where on the heating curve are we changing state?
Right there.
Oh, there's a flat line.
Alright, when there's a flat line. On flat lines, you are using the heat of vaporization, or for down here, it would be the heat of fusion. Now, specific heat is the energy needed to do what?
Go up 1 degree Celsius.
Raise the temperature within one state. So we're using specific heat on the diagonal lines. So on the horizontal lines, you're using molar heat. Diagonal lines, you're using specific heat. So diagonal lines use MCAT.
Wait, so which is the one that we use for heat fusion?
It'd be down here, this horizontal line.
No, like which formula?
And, molar heat times moles or grams.
Why?
I think it's the first one that you guys have. It's the molar heat of that phase change.
Okay.
See that how that's written there? Alright. So we're going to do a longer example. Okay? Because to calculate total energy, it is the sum of all the individual processes? Or processes?
Processes.
Process. Individual processes. Prophecies.
Processes?
Prophecies.
Whatever. Anyway, so the total is going to be the sum of each one of these line segments. Okay, so let's do a larger example here. How much energy is required to completely change a 4-gram block of ice at negative 10 degrees Celsius to a liquid at 25 degrees Celsius? So the first thing you should do is draw a heating curve and then figure out where your points are. So I've marked them with red lines. So we're starting as ice at negative 10. Okay, it's raising to the melting point, melting, and then heating up to 25 degrees Celsius as a liquid. How many line segments are there?
One. Oh, one flat.
3.
3 line segments. So there are 3 processes. It really feels weird to me, process. I don't know.
Or you probably change it to procedures.
That's different though.
Ew.
So the first line here is raising the temperature to the melting point. Right, then we're doing a phase change, we're melting, and then we're raising the temperature to 25 degrees Celsius. So for this first part, which equation am I using?
The first one.
Give me the actual equation.
M6CPT.
Great, MCAT. When I'm melting, which formula am I using?
The same thing.
No.
H total equals H process.
No. The one with molar
EH
heat.
process.
Right, the one with molar heat. Now, my molar heat of fusion is given to me in joules per gram. So it's going to be the molar heat times moles or grams.
Oh, during phase change.
If it's in joules per gram, I multiply it by grams. So the delta H of fusion times the mass. Because my delta H of fusion is in joules per gram.
I mean, where do you see that one on the paper? What's Q again?
Heat. Energy. Alright, then I'm raising the temperature from the melting point to 25 degrees Celsius. What formula do I use?
Q equals mass times
MCAT.
MCAT. Yeah.
So my total energy is each one of these Q's added together. So I have to do 3 calculations and then add them together.
That's complicated. And add them together. Oh my god.
So I'm going to go to the next slide where we actually calculate this out. Okay?
Are you going to give us the formulas on the test?
No, you have to know them.
Well, then,
It's 2 formulas.
But wait.
as long as it's not 30
Oh,
or
it's
40,
2.
I'll be satisfied.
What about the bottom one though?
That's just adding them all together. It's not
No,
even a real
total process.
Yeah, that's just adding them all together.
What does the big E mean?
Alright, it's a sigma, it means sum.
Oh.
Alright, so for the first part, my mass, Allie, my mass is 4 grams. My specific heat, since this is water, it's ice, right, is 4.18. My change in temperature, I went from negative 10 to 0. So final was 0 minus the negative 10. So 0 minus negative 10 is
Negative. Positive 10.
positive 10.
Yeah.
So 4 times 4.18 times 10 is 167.2 joules. That's the first line segment. The second one is where I'm undergoing a phase change. So that's the molar heat of fusion times the mass. So the 33.55 joules per gram times 4 grams, that gives me 1,334 joules. Now usually molar heat is in kilojoules. So what would I have to do if this was in kilojoules?
You have to convert it to joules.
You'd want to convert it to joules. Because you can't add joules and kilojoules. They have to be in the same unit.
3.
What's like the two dashes mean? So it's like 0 dash.
It's
dash.
minus a negative. Right, then the last one, I'm heating the liquid. So my mass is still 4.0. My specific heat is still 4.18. But now from the freezing point, or the melting point, to the 25, it's 25 minus 0. So 4 times 4.18 times 25 gives me 418 joules. That's just each individual line segment, okay? The total energy, so the total amount of energy required to do this is going to be the 3 of these added together, right? So the 167.2 plus 1,334 plus 418. That gives me a total of 1,919 joules. When I give you long problems like this, don't worry about sick bags.
Oh, thank God.
At all.
We have bigger fish to fry.
Fresh tobacco.
You guys are the worst.
Okay, so
Can we watch the link video?
what is T again?
Temperature.
So it's just, why do we subtract temperature when you just have it?
It's the change in temperature.
Oh, so it's going from 10 to 0, so it's adding.
Negative 10 to 0.
Yeah, negative 10 to 0, so it's adding that.
So that's a change of 10
So at the 25 is just, well, it's going from 0
to 25. So that's a change of 1.5.
You can put our answers in the
Doesn't matter. I'll know what you mean. All right. Let's go ahead and do this checkpoint real quick.
Oh my god.
We're just gonna do through number like 6, I think.
Why is the checkpoint so far?
Yeah, Dylan. We'll just finish this up. We're almost out of time. So on this graph, right, where is there only a gas present?
The top line.
Right, this top part up here is only a gas. Right, what about solids?
That flat line.
No.
The bottom.
The bottom diagonal is where solids are. What about liquids? The middle diagonal. Okay. In between, it's a combination of both. On the phase change, there's solid and liquid. On this phase change, there's liquid and gas.
Oh, I always thought, okay.
So, for this particular substance, what is the melting point?
1,500 degrees Celsius.
1,500 degrees Celsius, roughly.
What could this possibly be?
What about the boiling point?
Like,
The condensation point.
2750.
Whatever.
About 2750 degrees Celsius. That's really rough. Yeah, I didn't expect you guys to get there. Somewhere less than 3,000.
What is this substance?
I believe this is iron.
It can go into gas.
Oh, yeah.
You can get gas and iron.
I mean, that's at 2,750 degrees Celsius, so I think you're pretty dead.
Well, I don't think you're gonna heat with the iron. But
Just a thought. You're pretty dead.
can you? That means you can inhale iron.
No, you can't. You're dead.
Prove
Why
it.
would you be dead?
2,750 degrees Celsius.
Prove it.
Okay.
Do you know what degrees Celsius we're at right now?
Like,
25. 25.
But that doesn't mean you're with the iron in the.
But like as soon as it would get out, before it even like touches you, it's so hot they don't fry you.
Prove it. Let's do it
No.
right now.
No.
Right now.
Okay, moving on. Why is the temperature constant at the melting and boiling points?
Because
The energy
That's
is
but
like
doesn't it, like, do it back
focused
and
on
it can go up, but not to a point
changing
that
it.
it can.
The heat absorbed is overcoming intermolecular forces, not raising kinetic energy. It is changing potential energy, not kinetic energy. And temperature is a measure of kinetic energy. Oh, I was like, what did you?